So hello everyone and welcome back to this next lecture in the DC to DC converter series, and in this lecture I'm going to conclude on the SEPIC converter by doing an open loop control of the SEPIC converter. So as always, before we start this lecture, a brief background on this video lecture series and in general my objective of teaching power electronics online. If you are interested in these kind of video lectures but you would like something a little more comprehensive, I have a complete comprehensive online course on simulating power electronic circuits using Python on the MOOC website Udemy, and in this course I do complete more or less the entire process of simulating power electronic circuits. This includes how to install the software, how to use the software, a little bit of basic theory of power electronics, and finally a case study of how to simulate a buck converter. So this is a course on simulating power electronic circuits completely, and this is a beginner level course. If however you like something a little more on the signal processing and control side, I have another course also on the MOOC website Udemy, which is called Basics of Digital Signal Processing for Power Engineers, and this course is specifically designed for power engineers to be able to design filters digitally. So these are low pass filters, band pass filters. So this course has some basic theory of signal processing, and finally it has some case studies of how to simulate circuits, or rather simulate filters, by analyzing their frequency response characteristics and designing them step by step. All of this using Python. So with this I will get back to our lecture. So in the last lecture we had simulated, or rather we had analyzed the waveforms and we had plotted some results. Now we are going to go over and change the control file. So until now we were choosing a constant duty ratio. So we had started the simulation with a constant duty ratio of 0.3. So modulation signal is also the same as duty ratio as of 0.3, and later we had changed this to 0.6 to examine the difference in the waveforms between a low duty ratio and a high duty ratio. So now that this is done, the next step would be to bring in the open loop, or rather the open loop control file where I vary the modulation signal from 0 to a particular value. So for that I just have to go over to my file browser, go to the previous simulation, which is the Chook converter, and just copy over the open loop control.py and the open loop control _desc.py, DESC file. So this is a descriptor. So I will just come over to the SEPIC converter and paste these two. So all I have to do is add this file, and you see in this file I am changing the duty ratio from 0 to 0.8. So this is kind of emulating what would happen if you were to have a PI controller or some other kind of controller that is regulating the output voltage, and that regulation is done by varying the duty ratio. Of course this would not be done in such a way. You would take the feedback of the output voltage, feed it to a PI controller, and the output of the PI controller will form this duty ratio. Right? But I don't want to go into the detail of control because control usually requires much greater, deeper analysis. So this open loop control is what we will look at. So what will happen is I will comment out modulation signal and instead uncomment this line modulation signal is equal to open loop control mod signal, which is the variable storage element that receives the modulation signal which is derived in this particular control file. So let's go over to the web browser and let's go back to our control page and let us add this control file. So I just have to go over to my energy series, simulations, SEPIC converter, and here I will add the open loop control.py file, and I'll just call it open loop control, and I have to configure it. So for that I just have to upload the descriptor file, and with this all the variables are uploaded, right? Most importantly the time event variable, the static variable, and the variable storage element, right? You are of course welcome to add a control input and try to regulate the output voltage yourself by implementing a PI controller or some other kind of controller. So now that this is done, let's go back here, or let's go back rather to the main page and let us run this simulation. So let's go to the command line, make sure there is no error, so we don't see an error message, which means the simulation is indeed running. So now that the simulation is running, we can look at the output voltage plot. Of course, the simulation will take some amount of time to run before we get some understandable results, but this gives you an idea of what is actually happening. So as you can see, initially this is the very starting bit of our simulation, right? Simulation is just run for a few cycles, and initially the duty ratio is 0, right? We are starting with the duty ratio 0 and we gradually increase, right? And this you can compare with the previous cases where the duty ratio was constant. So which means that as the duty ratio increases gradually, our output voltage increases gradually, and that is only expected because as the time for which the device is turned on increases, the energy is gradually being transferred to the output, right? Of course, in our case, in the case of a SEPIC converter, if we go back to our circuit, when the switch is turned off, the input is connected to the output. This is very important. You see, even when the switch is turned off and the duty ratio is 0, the input is connected to the output. And since the input is connected to the output, there is an initial jump in the output voltage, right? So let's plot it again and see if it has progressed. It should have. And yes, it has. So you see, this is a progression, and you can see this clearly shows how the duty ratio is gradually increasing and finally steadies down to a certain value, right? And we can always confirm that this is the value which we should get, because remember, we have the computation for the output voltage, which is the input voltage multiplied by the duty ratio divided by 1 minus the duty ratio, and this is the final duty ratio, and this comes to 48. So if you have a look at this, we are at 40 volts, which means 8 volts is a drop across all the parasitic resistances, right? Now, of course, this probably raises a doubt as to 8 volts is quite a large drop, so we might need to adjust some of these values. For example, the resistance R1 could be decreased and some of the other resistance could be decreased as well, right? So this shows the gradual increase of our output voltage, and let's just quickly plot some of the others as well. So you see, these are the inductor currents, and let's go back to the file browser, and you see a very similar envelope in the input voltage itself. And this is actually very interesting because this shows how they crisscross each other, right? We saw this also earlier. We saw that for low duty ratios, the current I2, that is the current in this inductor, is larger than the current in the input inductor, right? We saw this in the previous simulations where we simulated with a low duty ratio, and we can actually see this in this envelope, right? The reason is very simple. We've already seen this. It's just the way energy is exchanged between the input and the decoupling capacitor, and the way the decoupling capacitor charges the inductor. And this is just a case of the parasitic drops across the resistances that are in this different paths in the circuit, right? So you see that eventually the current in the input inductor is much larger than the current in the output inductor, right? And this is only expected because the switch is on for 80% of the time. Therefore, the input inductor receives a significant amount of energy when the current charges up in the inductor, right? So with this, I'm pretty much done. We can simulate, we can plot several others as well. I mean, we can always plot them. Let's just quickly plot the capacitor current. But almost all of them will follow a very similar envelope. This is the capacitor current. And the capacitor current also has a similar envelope. Now, the capacitor current is bipolar, and that is only expected. The reason for that is simple, that when the switch is turned on, the capacitor discharges, right, in the counterclockwise direction, which means the current is flowing towards the left. When the switch is turned off, the input source and the inductor charge the capacitor, which means the current is flowing towards the right, which means the current in this capacitor is going to reverse every cycle, which is why it's bipolar, and that's why you see there is a positive peak and the negative peak, right? Now, it's quite obvious here when you look at the peaks that this shows that when the switch is turned on, right, and the switch is turned on for a large amount of time, the current in this capacitor is discharging, right? That's what it is, and we can actually verify, or rather let me go back to the web browser, and if we go back to our main page and the edit circuit parameters, let's check on the direction of the ammeter. So you see this is the ammeter and it is at one end. So you see this is the ammeter at one end and the positive direction is 1 ohm. The positive direction 1 ohm, which means the current, the ammeter measures a current flowing towards the right as a positive current. So if we come here and have a look, this shows that even though the switch is turned on for maximum amount of time, alright, so we know the switch is turned on for 80% of the time, but even with the switch turned on for 80% of the time, the current is much larger in the forward path during the remaining 20% of the time, right? Because when the switch is turned off, the input voltage and the inductor are charging the capacitor and the current is flowing towards the right, and that explains this positive peak, right? Whereas the negative peak is when the switch is turned on. The negative peak is when the switch is turned on, the capacitor discharges through the switch. So this shows that the energy available during the off time from the input and the inductor is much larger than the energy which is available when the switch is turned off. The reason for that is that the voltage source and the inductor, both of them, are charging this capacitor and the output voltage, right? So this doubling effect is what is boosting the output voltage and at the same time is charging this capacitor. So this explains how the energy is moving through this circuit, right? So you can see, you can actually, and I would suggest go in and zoom in on all these different parts. So you can see that as the envelope changes, there is a part for which the positive and the negative peaks are almost the same, and it is only for larger duty ratios that the positive peak is much larger than the negative peak. So this shows the boosting effect of the SEPIC converter. Alright, so with this, I think we've examined most of them, because we've examined the input, we've examined the output voltage, we've examined the inductor currents, the output voltage and the capacitor currents. I think this pretty much is almost all the waveforms of the SEPIC converter. You are of course welcome to go ahead and I'll just go back to the main page and stop the simulation. You are of course very welcome to go ahead and examine other plots as well as zoom in on those plots. But for now, I will end this lecture, and with this also the SEPIC converter lecture series. In the next lecture, we will go ahead and simulate another converter, which I will choose very soon, and I will start in the next lecture to start building up the circuit for that. So as before, since we are done with the simulation, let's quickly go and back up our simulation files. So I'm going to export the parameters. So once the simulation is running and is running satisfactorily, it is always advisable to back up all your files so that you now have the latest files that you can use for any particular, or at least to exchange with any of your colleagues. So in my case, these files will be provided. So with this, I have exported all the files. So that's basically one circuit parameter file and one control file, right? So once again, with this, I will end the SEPIC converter lecture series, and in the next lecture, next week, I will see you again where we will start another converter. So as before, if you have any doubts about what I did, please do post either in the comments or write me an email or message me on social media, whichever is your preference. Otherwise, I will see you in the next week. Thank you so much and see you soon. Goodbye for now.